Good morning. We'll get started here in just a second. Let me just finish writing some stuff down. Okay, good morning. Hey, sorry about last time. I had some technical issues with my computer. I did ask that everybody watch a couple of videos. I'm going to cover that material a little bit. I'm going to go quickly through it. So if you have any questions over that material, hopefully I'll be able to resolve that here today. And then I know some of you had some questions about the way that I had graded the exam. So on the exam, just so you know, I believe there were, what, 4 or 5 problems? I don't recall. Let me look at this real quick. Whoa. I didn't mean to do that. Okay, so there were 4 problems. So each problem was worth, the way I grade things is that everything is at 10 points. So there were 40 points possible on the test. And so if you got 40 out of 40, then you got 100. So if on your test I said like -7, then what you would do is do 40, take away 7, that would be 33. And then you would divide 33 by 40, and that would give you your percentage. So 33 divided by 40 would be a 70. Oops, I did that wrong. 33 divided by 40. That would be an 0.825, which I probably would have rounded up and made that an 83. And then I also added bonus if you did the bonus, or if you turned in the bonus problems that I had asked you to turn in. Okay, so I just want to clarify that. If we have any other additional questions about the exam, we can talk about that towards the end, or you can visit me during office hours. I'll be happy to go through the exam, your exam with you. Okay, let's get into today's stuff, which is going to be exponential functions. So I hope that you watched the videos. If you didn't, then you might want to go back and watch it, because again, I'm going to go through this quickly. The basic idea of an exponential function is that you have some number raised to the power x. And when you look at these graphs of these functions, they're either going to look like this or they're going to look like this. And it all depends on the number here, which we call the base. If that number is bigger than 1, then we're going to have this picture here, and we call this exponential growth. And then over here, we call this exponential decay. And you get decay if the number, your base, is between 0 and 1. So you just need to know that that's the basic look of exponential functions. So when you think back of all the things that we've learned how to graph, I think exponential functions are one of the easiest to graph. I hope you would agree, because all you do is make a little table, plug in numbers, use your calculator, and then you know it's going to look like one of these two. Now, one thing I did not talk about last time is a very special exponential function. So a special exponential function. And it involves a very special base. And here's the exponential function. We write it e to the x. And what you need to understand from this is that this thing e is actually a number. So I know a lot of you know that this symbol pi, we use this for like areas of circles, things like that. Pi is actually a number. It's about 3.1415, something like that. So pi is a very special number. We use a symbol to represent that number. E is also a number. It's a very special number in math, and it is actually approximately the number 2.718. And so when you look at this very special function right here, f of x equals e to the x, we call this the natural exponential function. And I won't get too much into the history of this function other than to tell you that we were looking, we meaning human beings, right? We were looking for a function that behaved a certain way, and we were looking everywhere for it, and we discovered it, and this was the one. And this is the only one that behaves this special way. So we give it the name natural because it just kind of naturally occurs that that's the function that behaves the way we wanted it to. You would have to take calculus to understand the true, I guess, beauty of this function. But we're just here to make sure you understand what it is and what it looks like. So can somebody tell me whether or not this function would represent exponential growth or decay?
Growth.
Growth. Why would this be growth?
Because it doesn't have a negative, like it's not greater. It's greater than 1.
That's right, because the base here, e, right, we're saying is about 2.718. And I just said here that if we have our a, if our base, right, is bigger than 1, then we're going to have this growth. So another way you could look at this is by saying that this is f of x equals 2.718 to the x. But the thing is, your calculator has a key on it for e. So what I'd like us to do right now is I'd like us to graph this. Okay, I want us to graph e to the x. So to graph it, I'm going to make a t-table. Here I'm going to put x, and here's going to be e to the x. And like I said in the video, what I want you to always do when you're graphing exponential functions is plug in these values. Everyone's going to do the same thing. We're all going to plug in the same values of x every single time we want to graph an exponential function. So that means we need to do e to the -3, e to the -2, e to the -1, e to the 0, e to the 1, e to the 2, and e to the 3. And we're going to need our calculators to do these. All right. Well, we need our calculator with the exception of this one, e to the 0, because any number to the 0 is 1. So I can put that to 1. But otherwise, I'm going to need my calculator. So please, at this time, use a calculator to try and figure out what e. You have to find your e button. And what you'll want to do is do e to the -3 power. Now I'm going to tell you what the answer is, and hopefully you'll be able to get this on your calculator. 0.049. Let's just do that. 0.049. Now would be a good time. If you're not able to get that on your calculator, now would be a good time for you to, let me know. Is anyone having trouble getting that? I'll keep filling out this table. E to the -2 would come next. I get 0.135. E to the -1 would come next. I get 0.367. E to the first power, just to the 1, would be 2.718. We already kind of knew that. E squared would be 7.389. And then finally, E cubed would be 20.085. So now if we go to graph this, we know this is going to be exponential growth. So we know the graph is going to kind of look like this. But let's get a little more detail on that. And so what I'm going to do now on my graph is I'm going to go to the right. I'm going to go 1, 2, 3. To the left, -1, -2, -3. And then I'm going to start plugging in or plotting my points. But I'm also going to keep in mind here that the highest value, the biggest value I have is 20. So that means I'm going to put this up here, like way up here, that's 20. And then that means this would be about 10, maybe 5, 15. And now we're just going to like kind of estimate where things are. And I think I'll start out with this point 0, 1. So if I plot that point, that means I go to the left and right. I don't go anywhere left and right, I just go up 1. And then when I plug in 1, I get 2.718, which is, I don't know, somewhere around here. When I plug in 2, I get 7 point something, which puts me about here. When I plug in 3, I'm way up at 20, like that. And then what I'm going to do is just connect those together. And then the other points, all I need to know is that they just get smaller and smaller. So this is where we have our horizontal asymptote. So it kind of flattens out over here. Just like it did with the rational functions. It's like a magnet that pulls the function down, but just on one side. It doesn't do it on both sides, just one side. And so that would be the graph of e to the x. The big thing that you need to be able to do here is this on your calculator. You must be able to do that part. That's the important part of what I'm showing you right now. Okay, any questions on this? The special exponential function? The natural exponential function? No? Okay, I'm gonna show you another special one. Okay, this one right here is like the most special. All right, this next one is special, but it's only special for well, I'll tell you why. Special exponential function. Okay, another one. I'll put that. Another special one. We only have 2 special ones we're going to look at in here. And it's this one. F of x equals 10 to the x. 10 raised to the x. And this is called the base 10 exponential function. Oops. Now, I'm not going to do the table, okay? We could do the table. All I want you to know here is that this is also exponential growth, okay? Because the base here is 10, and 10 is bigger than 1, so we should have growth. Are there any questions? Okay, I'm going to show you something here. Oh, where'd everyone go? Okay, so I'm going to show you something here. I'm going to have the computer graph a to the x, and I'm going to create this thing called a slider, so I'll be able to adjust the value of a. So right now, let's make it e, all right? That's the graph. That is the graph of e to the x right here, all right? So e is about 2.718. That's what I told you, right? So e is about right there. That's what e looks like. 10 to the x is going to be, the base is going to be bigger, right? The base is 10. So what happens when I make this value of a bigger? So look at the graph. See how it just gets steeper? And that just means that the graph grows faster. So what I want you to understand is that the bigger a is, the faster it goes up. The smaller a is, it still goes up, but just not as fast, right? And then if a is between, I have to make sure I don't go past 0 here. If a is between 0 and 1, watch what happens. This is when the graph flips to the other side. You see that? And then it goes this way. So the smaller a is, the steeper it is the other way. So all I want you to see is just the relationship of how a impacts things. Positive, a bigger than 1, we're like this, growth. A between 0 and 1, we have decay. Okay. All right, now, that's it with exponential functions as far as graphing them. I give you an exponential function, you create the table, you plot your points, you're done. But all of that was leading us into applications, which I talked about simple interest. So these are going to be word problems, and these are kind of fun, I think. Simple interest. And simple interest has to do with how much money you would have in an account if you left it there and let it grow, right? If a bank is giving you interest. Or on the other hand, if you owe money on a credit card, how much interest you're getting charged to borrow their money. And I talked about how banks work, right? So the two main formulas that we have here are these two. A equals P times 1 plus R divided by N raised to the N times T. That's the first formula we have. The second formula we have is A equals P times E raised to the R times T. So those are our two formulas. I'll call it Formula 1 and Formula 2. And I talked about in the video what all of these letters represent. So I'm going to just write those down again. T is equal to the time that the money is left in the account. And this is always measured in years. R is the interest rate. And then let's see, P is what we call the principal. This is the starting amount of money. And then A is the money after T years. And then the N in the problem is the number of times the interest is compounded. Per year. All right, so we need this information to be able to answer the following questions. So the big idea again here is that you're imagining that you're going to either be putting money into a bank for a certain amount of time at a certain interest rate. And the question is, how much money will be there at the end of that time? So let's say, you get $5,000 and you put it in the bank at a certain interest rate, and you're going to leave it in there for 3 years. You want to know how much money is going to be there after 3 years, right? That's the idea. Or if maybe you go to Best Buy and charge, go buy that stereo system you wanted, and you buy the TV you wanted, and you spend like $3,000 at Best Buy, and you do it on a credit card, and they have a certain interest rate. This will help calculate how much money you will owe at the end of a certain amount of time. Okay, so these formulas are actually used all the time, but there's two different ones, and there's slight differences between the two. So that's what I want to make sure everyone understands here after we get through these examples is when is it that you use the first formula? When is it that you use the second formula? What's the big difference between the two? So I think best thing to do would be to just do an example. All right, so let's say that we put $5,000 into a simple interest account. So maybe it's a savings account. I don't know, maybe you put it into like some other account that gives you a decent return. Let's say we put in a simple interest account at, let's go 2.3%. And we do this for, let's leave the money in there for 4 years. Okay, so we have $5,000. We're going to put it into an account, try and save some money. 2.3% is the interest rate. And we're going to leave it in there. We're not going to touch it for 4 years. Let's see how much is there at the end. Okay, so the first question is how much is there if interest is compounded monthly. The second question is how much if interest is compounded let's go quarterly. And then last, how much is there if interest is compounded continuously? Okay, so this idea of the interest being compounded is usually very challenging for students to understand. So let me try and make it make a little more sense. When we say that the interest is compounded monthly, what we're saying is that the bank is going to look at the money every month, and they're going to give you a little bit of money for you having your money in the bank. So they're paying you for your money. And if they compound it monthly, then they're going to look at your money every month, and they're going to give you a little bit every month. But the catch to it is that they're not giving you 2% every month. Okay, they're not giving you 2% every month. They're giving you not 2.3%. They're not giving you 2.3% every month. What they're doing is they're taking that 2.3% and they're cutting it into 12. They're dividing it by 12 because they're doing it monthly. So it's 2.3% divided by 12, and they're not doing it on all of your money. They're only doing it on a fraction of your money, on 1/12 of your money. So it's not as good as it looks because they're dividing everything by 12. But the formula we use for that will be this first formula right here. Okay, we're going to use this formula here to calculate that. So let's just do part one. All right, let's just do part one, and then we'll get to part two. So for part one, we're using this formula. And I think I'm going to call on some people because I just feel like having some participation today. Oops. All right, here we go. Where should I start here? Is Denise here? Denise?
Yes.
Yes. Okay, Are you following? Do you have any questions right now?
No.
You okay?
Yeah.
Okay, so can you tell me what parts of this I can fill in? So maybe on the side here, tell me, do we know what P is for us in this formula?
Yes.
What is it?
That's 5,000.
5,000, right? That's the amount that we're going to start with. Okay, good. Do we know what R is here?
Yes.
What is it?
2.3%.
Okay, and so anytime we get R, we always want to convert it from a percentage to a decimal. We never want to plug the percentage in here. We always want the decimal version of it. So Denise, what would that be converted to a decimal? You remember what to do?
Yes.
Okay.
0.023.
Yep, 0.023. Good. Is everyone clear on that? Convert that right to a decimal. What else do we, oh, time, I forgot time. Do we know how much time we're leaving it in there for, Denise?
Yes.
Okay, go ahead.
4 years.
4 years, okay, good. So we have what P is, we have what R is, we have what T is, we still need N. So N, Denise, comes from, N is the number of times the interest is compounded per year. And in part one, it says it's compounded monthly. So how many times a year would that be, Denise?
48.
Okay, good. I'm so glad you said that. So I think what Denise is thinking is, okay, it's compounded monthly, right? Which is 12 months every year, but it's for 4 years. So she's thinking, okay, 12 times 4. Actually, in the formula, N is always just the number of times per year, not the total number of times they're going to do it. So I'm glad you said 48 because that's the most common mistake students make. we're actually just going to put 12 there. Okay, it's always just, you're only looking at 1 year. Don't worry about the 4 years. The 4 years will be taken care of in the formula. Okay, the 4 is going to go here, and that will take care of it. Clear, everyone? Denise, that good?
Yeah.
Okay, all right, good job, Denise. We'll move on. So at this point, I'm just going to plug everything in. Okay, so the amount that we have in the account will be equal to P, which is 5,000, parentheses 1 plus the rate, which is 0.023, divided by N, which is 12. All of that raised to the N, which is 12, times the T, which is 4. Any questions on that part? No? Sure? Okay, I'm gonna get on my calculator right now. I'm just gonna figure out what that is. And I'm gonna figure out what that is, and I'm just gonna rewrite everything. So this is 5,000. 1 plus, okay, I get on my calculator, I do 0.023 divided by 12. And I get 0.00191666. Okay, so here's the first time in our class that I'm going to ask you to just go out with the decimal places. Go out as far as your calculator goes. But you don't need to go past, like, maybe, how many do I have here? 6, 7. 7 digits is fine. But don't round this to, like, do not round this to 0.001, okay, or 0.002. Go out further, all right? The more decimal places you go out, the more accurate your answer is going to be. And then up on top, I do 12 times 4, that's your 48. Any questions there?
Yes.
What you got?
Couldn't you have just gone with the initial 48?
Say that again?
Couldn't you have gone with the initial 48 that she said?
I'm not sure. You just sound, I can barely, like, understand you.
He's
Couldn't you have
asking if she could have just used the 48 from the beginning, since she multiplied the 4 times the 12 anyways.
Are you, so just not write 12 times 4? Is that what you're saying? Oh yeah, you don't have to write it. I just want to make sure everyone understands where every piece of the formula is coming from. Yeah, like that N is the 12, the T is the 48. I mean the 4, that becomes the 48.
Wait, I'm sorry. When I divided the 0.023 divided by 12, I got 0.001917.
Okay, so yours rounded to 17. That's okay. Just use that. That's all
Okay.
right. Yeah, everybody's answer is going to be just slightly different, and it's going to depend on their calculator. All right. But I promise we'll all be within probably a couple of pennies of one another with our answer, right? Because our answer is going to be an amount of money. So we should all be pretty close, within $1 of one another, hopefully. Okay, so order of operations. Let's do this first. We've got to do what's in the parentheses, right? Do not try and multiply that 5,000 through. So 5,000, when I add 1 to that, all I get is 1.0019166 raised to the 48. The next operation, order of operations, is to do this thing to the 48th power. And you've got to be able to do that on your calculator. And like I've said before, everybody's going to have a slightly different way of doing this on their calculator. So you need to make sure you know how to take that, on your calculator, how to take 1.0019166 and raise it to the 48th power. I'm going to tell you what answer I get, and hopefully yours is pretty close to this. 1.096264. And again, you can go out as many decimal places as you want with your calculator. Does anyone have a question on that or have trouble on their calculator getting that? No? Now just multiply 5,000 times that. I get $5,481.32. Now, if your answer on your calculator has more digits, like maybe it's like 1, 5 or something like that, what we want to do is just throw out the last two numbers, because remember, this is money. And so we can't have anything past 2 decimal places, because that's our pennies, right? 32 cents there. So that's our answer, $5,481.32.
You said it didn't matter if we were off by a little
Yeah,
bit,
if
right?
you're off by a couple of pennies. What did you get? Did you get something way off, or?
No, you got 32 cents. I got 34 cents.
Yeah, okay, so we'll be within a few pennies of one another, and that's okay. Okay. All right, so if we put $5,000 away at 2.3% interest and we leave it in there for 4 years, we will have gained. How much money did we gain? Looks like what, $481 about? That's how much money the bank gave us to borrow our money. Okay, but we couldn't touch it. It's very important. We weren't allowed to take any money out, right? We could not touch that money for 4 years. I don't know, is that good or bad? I mean, it's like $120 a year, about, right? And we got about $480 from the bank total. We did that in 4 years. So if you look at that, that's about $120 a year we got, which is about $10 a month. So that's how much the bank paid us to borrow our money, $10 a month, just about. Okay, now let's look at the second part of this problem. Second part is the same exact thing, except we want to compound the interest quarterly. So what does it mean to do it quarterly? You don't know what that means, to do it quarterly?
Does it mean like 4? Like 4, like the
How often is
Every
that?
3 months.
How many
every
times
3
a year would it be if it's done quarterly?
4.
Isn't it every 4 months?
Right.
3.
Every 3.
Okay.
So, but it would be 4 times a year. So quarterly means 4 times a year. All right, so we have to know that, because on the test, if you see quarterly, you have to know that that means 4 times a year. So all we're gonna do for the second part, the only thing that changes is that n now becomes a 4. Everything else in the formula is exactly the same. Okay, so I'm gonna do this on a new page. No, that's not what I meant to do. So we're using this formula. And the only difference is that n is 4. Everything else is the same. So that means it's going to be 5,000. The amount that we'll have is 5,000. 1 plus the same interest rate, 0.023, divided by 4 this time, and then 4 times 4, because n is 4 this time. So the only thing we changed was this and this. Instead of 12 there, we put 4s. And that's going to change our answer. So what do y'all think? Do you think we're going to get more money from the bank or less money? What do y'all think? If they're compounding the interest less frequently, do you think it's going to be more or less money for us? Any guesses?
More.
You think more? Okay. Let's see. Let's calculate it, right? 0.023. Let's divide it by 4. So I'm doing this operation first. I'm doing that on my calculator. And I'm going to save us just a little bit of time. I'm going to go ahead and, when I get that answer, I'm going to add the 1 to it also. So I'm going to add 1, and I get 1.00575 there, and then raised to the 16. Make sure you multiply the 4 times 4, right? Now I take this and raise that to that power in my calculator. Raise it to the 16th power, and here's what I get. 5,000 times 1.096075, something like that. Again, we're going to have slight differences in our answers because of where we decide to round things. but all of our answers should be within a few cents of one another. Okay. Anybody want to share with me what they got? Or what they get?
I
5,000.
got 5,480 and 37 cents.
37. Yeah, I got that too. I got 37. I got 375, but I could leave that as 37 or 37, 38. Doesn't matter. We just need to be pretty close. So I think I agree with that. Okay, so let's compare that. How much money did we make from the bank when they compounded monthly? $5,481.32. And here it was $5,480.37. That's like less than $1 difference, right? It's a little bit less. It's a little bit less. And the way it turns out is that the fewer times they calculate your interest, so the smaller the n is, the smaller the amount is that comes to you. The bigger n is, the bigger it gets. All right, but there's a limit to how big it can get. And that's what the last problem here is about. The last one is saying, how much will we have if the interest is compounded continuously? And this is a very difficult concept to explain because it doesn't make a lot of sense. What continuously means is that the bank is calculating your interest all the time. Like at every instant of every day, I'm not saying daily, I'm saying at every instant in time, they're calculating your interest. Okay, but they're doing it on like this infinitesimally small fraction of the percentage. It's a very difficult concept to explain because it requires doing calculations an infinite number of times. And then to do that, you need to understand calculus. However, there is a formula that will do that for us. And that's this formula right here. And that's the indicator to you that you need to use this formula is the word continuously. As soon as you see the word continuously, you know you're going to that formula. All right. We only do the other formula when they tell us how many times it's compounded, like monthly, daily, quarterly. Okay. If they give us an actual nice number, we can put it in there. If it's continuously, we use that formula. So let's do this part 3. I'll put it, I'm going to just squeeze it in right here. So for part 3, we're using the same form, not the same formula, this formula. And notice on this formula, which in the video I call it the shampoo formula, right? Can I call that? Hold on just a second. Time out. Let me go get a drink. Y'all try and see if you can figure out how to do it. I'll be right back. All right, so check it out. Just in case you think I'm lying to you, right? Check that. That's why my hair looks so good. You see? It's PERT. It's the way to do it right there. So this is our PERT formula, right? The E here, the E in the formula is the E we were just talking about a second ago, right? I said there's a key on your calculator. Notice that in this formula, there's no N, right? There's no N. So we know what P is, right? P is the 5,000. Then we say times E raised to the R, which is 0.023, times T, which is 4. Does everyone understand where these pieces come from? 5,000 is the P, R is the interest rate, T is the time, and E, well, that's what happens when we compound continuously, all right? We don't have an N anymore. So now what I'm gonna do, first thing I'm gonna do is I'm gonna calculate, on my calculator, I'm gonna do 0.023 times 4. My wife makes fun of me because I use PERT. I only use it because it's a math formula. That's the only reason I use it. Okay, everyone okay? 0.023 times 4? That gives us 0.092. Now on my calculator, I'm going to do E raised to the 0.092. This is why I said earlier, it's important that you're able to do this table because you need to know how to raise E to different powers. So now on your calculator, do that. Does somebody want to tell me what they get when they do E to the 0.092? Someone want to share that with me?
1.09636. That's what I got.
636. Okay, that's good. My calculator goes a little bit further than that, but I'll stick with that. And now multiply that times 5,000. And we're going to get $5,481.80. And that's our answer. And that is the most amount of money you're going to get from a bank ever, is if they compound it continuously. And what's nice about the continuously formula is that you just use that E key on your calculator. It's pretty straightforward. Once you get this, just do E to that power, you're done. You don't have to worry about this fraction. Now, isn't this the most we've gotten so far? This is definitely bigger than that, right? And then when we did it monthly, it was 54.81.32. So we had 32 cents here. Here we've got 80 cents, so a little bit more. So this is the best case scenario for us. Most banks use this formula, okay? If you get out like a credit card statement, or when you sign up for a credit card, all that little fine print, it'll say in there that they compound interest continuously. And that lets you know that they're going to use that formula. Any questions? Okay, let's do something else. How about we look at this from another perspective? Instead of us putting money into a bank, let's see what would happen if you owe on a credit card. All right. So I'd like to know, I want you all to kind of help me form this problem. All right. So let's say you get a credit card, all right, and you go out and you go crazy and go spend a bunch of money on this credit card. So someone tell me, how much do you want me to say we charged up on a credit card? Whatever amount you want. First answer I'll take.
I don't know. I don't know what the average amount is.
Well, not an interest. I'm not asking for an interest rate. Just you went crazy shopping, okay? And
Okay.
and we wouldn't be doing
$3,500.
that. How much?
3,500.
Okay, $3,500. All right. So we went out on a little shopping spree. You charge $3,500, okay? On a credit card okay, so let's talk about interest rates. Do you all know what the interest rates are on credit cards? They vary, don't they? They're not all the same. What do they look at to determine your interest rate for your credit card? Do you know what they look at?
Isn't it your credit score?
Okay, yeah, this thing called your credit score. Do y'all know do you know what a credit score is?
I know it's like,
Go
I
ahead.
know it's kind of based off of like how reliable you are with like borrowing money, and if you pay it back at a like
Mm-hmm.
reasonable amount of time.
Yep. Yeah. So every person, at some point in your life, you start to establish your credit. Okay. And your credit is basically like your reliability. Okay. And what they look at is they look at your income, they look at your expenses, they look at they look at how many credit cards you have open. They look at how much money you owe on each credit card. Have you ever missed any payments? All these different factors they take into account, and they give you a score. All right. And that score can be between, let me look it up, credit scores. I forget what the highest is. I think 800 is the highest.
850.
850. Okay, so 850 is your highest, right? So, and yeah, well, I could get lost in the internet here. I'm not going to go. All right, so poor credit scores, you know, you have like categories, like anything from like 800 and up is really good. And then, you know, you start going down to lower, like 750, 720. So your credit score is going to determine your interest rate a lot of times. And this is especially important if you go to buy a car or a house. They always look at your credit score because they want to know, is this person reliable? Are we going to get our money back? So with credit cards, even if you have a really good credit score, interest rates on credit cards are always much, much higher than a bank is willing to give you if you give them your money. Like if I just go to a savings account right now and I go put money in there, you know, on the example we just did, I put 2%, right? 2.3%. That's never going to happen at a bank. Does anyone know what banks' interest rates are for, you know, how much they'll give you? Does anyone have any idea what it is? Anybody here work at a bank or no? It's way below 1%. It's not even 1%, okay? It's below 1%. No matter how good your credit score is, you go to a bank and put money into a savings account, you're going to get less than 1% back. All right, which is terrible. But if you go borrow money from a bank, use a credit card, your interest rate is going to be extremely high. Now, I have a credit card. I only have one credit card. No, I have a couple, but I only have one that I use on a, you know, on any basis. And I have a good credit score, and my interest rate on that card is 7.1%. That's very, very, very low for a credit card. Most credit cards are going to be 16% and higher. So I've seen them as high as 23%, 24%. And again, a lot of it depends on your credit score. So let's say that we go charge this up. Let's say we got credit score. So let's say we do this at 18.9%. I don't think that's unreasonable, okay, for like most people, all right? So we go charge it up. Now, we're supposed to make monthly payments on this, right? But just for the sake of simplicity, let's just act like we don't do anything on this credit card. We don't make any payments for 3 years. Now you're going to get penalized and all this other stuff, but let's just, the penalties aside, how much would we owe after 3 years? So how much would you owe after 3 years if interest is compounded monthly? How about continuously? So we're just going to compare two different ways. If they compound our interest monthly versus continuously, and I'm going to do this to one case on one side, the other on the other. So first one, we're going to have to use the formula, the non-shampoo formula. And on the other side, we can use the shampoo formula. All right, let me call on somebody. Okay, Emily, is Emily here? I see Emily.
Yes, I'm here.
Okay. I don't know if you've responded already today, but
No, I haven't.
you're next on the list. Okay, any questions about these formulas, Emily? And why I'm using those? How about on the first one, Emily? Can you tell me the things that we have here? Can you tell me P? Can you tell me R? Can you tell me T and N?
So P would be the 3,500.
Yep.
R is the interest rate, so the 18.9%.
Okay, so what do you want me to use for R?
0.189
Yep, 0.189, good. And then T,
is the 3 years.
3 years, and then N,
It's asking for a monthly, so it's going to be 12.
good, perfect. Everyone got that? Okay, now we plug in 3,500, 1 plus R, which is 0.189 over 12, and then 12 times 3. So I'm going to work a little faster here. I'm going to go ahead and calculate what this is. So I'm going to do 0.189, divide that by 12, and then add 1. So 3,500, and this is 1.01575 raised to the 36, because you have to multiply the 12 times 3. I'm going to go ahead and let you calculate this. Is Sebastian here?
I'm here.
Yeah. Do you have a calculator? Are you able to calculate this?
Yeah, do you just want me to give you the answer?
Yeah, give me the final
Okay.
answer. What'd you get?
Okay, I got 109. Did I do that correctly?
Something, I hope. Yeah, that's
Let me.
Did you raise this to the 36th power?
Oh, I forgot to do the raise sign. I just times it by 36.
Ah, okay. Yeah.
So I'm gonna do that. 1.755197.
Okay, and then go ahead and take that answer and multiply it times 3,500.
Yeah, let me do that. 3. Still giving me a weird answer.
You had the 1.7551. That was right. 1.75519, something like that.
But
Take that mul-
$5,265.59.
Okay, good. That sounds about right. Wow, that's a huge difference, isn't it? In 3 years, you went and charged $3,500. That was a great day. You were just buying all the stuff you wanted. But if you don't do anything about that money in 3 years, that's going to be all the way up to $5,200. That's growing pretty rapidly, and that's because the interest rate is just so high, right? Your interest rate is just so high. Now let's do the same thing over here. Let's do the continuously. So the only thing that changes here is that we're going to use the different formula. And it's very important that you're able to do these calculations on your own. I mean, I can show you how to set it up, but you've got to be able to do this on your own, on your calculator. So I'm just going to give you the answer here. Wow, is that right? Wow.
I had gotten a different answer for the other.
Did you?
Yes.
Yeah, I'm sorry. I was multiplying it by 3,000 the whole time, not 3,500.
Oh, okay. All right. Okay, so you got something different here, Carolyn?
Yes, I got 6,143 and 20 cents.
6,143 and what?
20 cents, but I got mine doesn't round as much as the other like your calculator, so I got 20 cents.
That's
So
fine.
some people might be
So
off.
we're pretty close, right? We're pretty
Yeah.
close to this. Holy shit. Okay, so it's even higher than it looked like initially. Wow. Look at that. I mean, at 18%, You don't pay that back, man. You're going to owe like over $6,000 in 3 years. That is insane. That's why banks are willing to give you a credit card. They're willing to take this. They're willing to let you borrow money, because when you finally do pay it back, you're going to be paying back so much more than you ever borrowed that it's worth it to them. So think about it this way. Let's say I have $10,000 right here, okay? I could go put it into a bank, right? And they're not going to give me anything for that money to just sit there, right? But if I put that, if I were able to somehow take that money and loan it to somebody at a high interest rate, then I'm going to get that, I'm going to get a lot more money back, but I have to wait for it, right? I'm not going to get it immediately. It's going to take time. And that's what banking is all about. They take people, I showed this in the video, they take money in, right? They say, hey, let us keep your money. We're going to give you a little bit of money for that. Then they go loan it to people and ask them to pay back a lot more. So that's how the bank makes money. Now, this one over here, I didn't finish writing it. This gives you 6,170.39, something like that. So those are the two cases. I don't remember in the video, did I talk about lottery winners? I did, right? Winning a lottery? No? Thought I did. Okay. Well, are there any questions on this? No?
Yes. So the only time we're going to be using the PERT formula is when we're going to when it's compounded continuously.
Yep. The only time you use that is when you see the word continuously. All
Okay.
right.
Thank you.
Every other time you're going to have an N. So the N's that you should know are monthly, which is 12, quarterly, which is 4, and then those are the only two I'll throw at you. You could have daily also, but then N would be 365. So, all right, now in terms of the homework assignment that I gave you all last time, let me just take a look at that real quick. Oh, here we go. So I need to bring up the packet real quick. Page 147. So I asked you to do page 147, problems 1 and 2, so graphing these. So all I wanted you to do here was make a t-table, -3, -2, -1, 0, 1, 2, and 3, and then create the numbers and then draw your graph. I wanted you to do that for number 1, and then I wanted you to do that for number 2. And then the other thing I wanted you to do was page 148, 5, 6, 7, 8, 9. So 148, 5, 6, 7, 8, 9. So on this, you couldn't really do this problem, right? Because I hadn't talked about continuously compounded interest. So now you should be able to do you should be able to do number 5, because you're putting this money in, you're given an interest rate, it's compounded continuously, and they give you 5 years. Do you see now that you can do that? And then the next one, okay, 6 is money is invested, interest rate, compounded semi-annually. What does that mean? Semi-annual means how many times a year?
Is that 2?
Twice.
It's 2. So this would be n is 2. So now you're not using the shampoo formula, right? And they give you the number of years. The next one, 1,000 invested, 8% quarterly. So n would be 4. They give you 10 years. And the last one is continuously. So you use the shampoo formula. Let's make sure, was it, oh, it was 9 also. Yeah, you know what? Let's skip 9 for now. Let's skip 9 for now. Okay. We're not quite ready for 9. All right. I hope that that kind of helps clarify some of the stuff. I know, watching a video is a little different than being, present. Are there any questions on this? Okay, so we have about 15 minutes left. I'd like to just discuss a little bit about the next topic. We'll probably just trying to think here of how I want to do this. Yeah, we have a major concept that we need to discuss. So we got the shampoo formula. We got that formula. We talked about the natural exponential function. Okay, I just want to make sure I'm not missing anything here. All right, good. All right, so let's just, I'm going to introduce this idea, and that way when we get into it next time, hopefully it'll make a little more sense. So I want to talk about what are called inverse functions. So I want to start with a function that everyone here would be familiar with. F of x equals, let's say, 2x. So what this function does is it takes something in and it doubles it, right? So if I were to draw a picture of this function, the function f would, let's say, take the number 1. And where would it take the number 1? Take it through and become what? 1 becomes 1 times 2 would be 2, right? It'll take the number 2 and double it, and it'll come over here and become 4. It'll take the number 3, comes through the function and becomes a 6, right? That's pretty straightforward. Just doubling whatever is going in. This is the input. Whatever comes out is just twice as much. So the function that we're looking at here is f. Now what I want you to consider is there a function that would take everything back to where it came from? In other words, if the input was this, the output is this. So if I plug in 6, I want the function to spit out 3. If I plug in 4, it needs to spit out 2. If I plug in 2, it needs to spit out 1. Can somebody tell me what function would do that? So if the direction from the left to the right is doubling, right? We're doubling to get from the left to the right. To go backwards from right to left, we would have to do what?
Divide.
Divide, right? Cut it in half, wouldn't we? We'd have to take whatever this is and cut it in half. So I could write that function, and watch the way I write this. F with the little -1 up here, and I could say 1/2 x. So think about this. This little -1 tells you that this is the inverse of this function. It's the inverse of that function f. It undoes what f does. F doubles everything. The inverse function halves everything. And if you don't believe it works, try it. If you were to plug in 6 to this, 1/2 of 6 would be 3, right? So that shows that that 6 would go back to 3. And you can do it for all those numbers. 4, take half of 4, you go back to 2. Take 2, take half of that, you go back to 1. Does that make sense? The idea of an inverse, all it does is undoes some other function. Yes? So what about this function here? Try this one. X squared. Think about what that does. Takes number 1, sends it over to 1 squared, which is 1. Takes number 2, squares it, 2 squared is 4. Takes number 3, 3 squared is 9. Takes number 4, 4 squared is 16. What would the inverse function need to be to go backwards? To go from 16 to 4, 9 to 3, 4 to 2, and 1 back to 1.
Be the square root of x.
That's right, we would need the square root of x. We'd have to undo, so we f squared it, right? So to undo a square, you take the square root. The previous example, f doubled the input, and so to undo that, we need to take half of the input. Okay? Is this making sense? Any questions? Because I'm about to show you something that's going to be very weird. But you have to have this basic idea down first. Okay, let's look at this function. This is where things are going to get weird. F of x is 2 to the x. That is an exponential function, right? We just started talking about these. Let's take a look at what it does. Takes number 1, 2 raised to the 1 is 2. Takes number 2, 2 raised to 2 is 4. Takes number 3, 2 raised to the 3rd is 8. Takes number 4, 2 raised to the 4th is 16. I hope y'all understand that all I'm doing is like a little t-table here. I'm plugging in 1, 2, 3, 4, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st power, and that's how I'm getting these answers. So, can anybody think of something that would undo this? That would take 16 back to 4, 8 back to 3, 4 back to 2, 2 back to 1. Well, if you think about that, trying to go backwards, it's not easy. We're not doing the square root, right? Like it works here. The square root of 16 is 4. Great. But the square root of 8 is not 3. So it can't be a square root function. We're not doing half of it, right? It's not half of 16. So do y'all see that there's not a clear path backwards? Do y'all see that? There's not a clear path backwards. And it turns out that there is no function to go back unless we introduce a new type of function that you've never really worked with before. Okay, so right now, there is no way back. Okay, there's no way back. There's no inverse. We have to introduce a new type of function. We need a new function, something you have not worked with before. And the name of that function, or those functions, they are called, they have a name, logarithmic functions. They're called logarithmic functions. So we talked about exponential functions in the videos that you were supposed to watch, and today I talked about exponential functions, but now we're introducing a new type of function, and they're called logarithmic functions. And I'm going to just tell you that historically, when I've taught college algebra, logarithmic functions cause the most problems for students because it's a different notation that you haven't seen before. And so everyone gets freaked out by the notation. So I'm going to try just, again, we only have 5 minutes. I'm just going to introduce you to the notation. All right. So we'll get back to logarithmic functions. I'm going to now write something down and I just want you to look at it. Okay. I'm going to write the word log. Okay. L-O-G. I'm going to put a little subscript below that and put a little a here. And then here I'm going to put x and then I'm going to say equals y. What you're looking at here is what we call a logarithmic equation. All right, so this is just purely notation. All right, we have this new thing, this log, and then we've got this subscripted a, and then we have x, and then equals the other side y. Now, what the hell does that mean, right? Like, what does all this mean? Here's what it means. This equation means that a raised to the y equals x. A raised to the y equals x. All right, so I understand that this looks weird. Okay, I understand that this all looks weird. So let me try and explain this with an example. If somebody were to write log 3, 9, can somebody tell me what this would be equal to? So what does this mean? What does this mean? And you know what, yeah, okay.
It equals 2.
Okay, why is that equal to 2? That is correct. Why is it equal to 2? Well, think about what this is saying. This right here means, what does this really mean? This means that when I look at the a, which is that number there, which for us is 3, and I raise it to the y is the answer, I should get the x, which is the 9. And that is true. 3 squared is 9. I understand that this is confusing. So I like to look at it a different way. When I present this to my students, I introduce them to this idea, which I call the loop. Okay, the loop. Look back up here at this first expression I gave you. I want you to draw a loop that goes from the a to the y and then loops back around to the x. Y'all see that? It's like a loop that goes like that. The loop says that when I take a and I raise it to this power, it should equal whatever's there. So look at this right here. This means that when I take that a and I raise it to the y, a raised to the y, I should get equal to whatever's there, x. So back here at this problem, well, I'll leave that there. When I wrote this down, log 3, 9, when I wrote that down, we were trying to figure out what that was. So let's call that side y. We don't know what it is. And now if we do the loop and just write down what the loop is, 3 to the y equals 9. Now you're just asking yourself 3 raised to what power is 9? And then you have to think through that and understand that that's 2. Okay, we're out of time. We're going to do more of this. I really just wanted you to see the main idea here is that when we have an exponential function like 2 to the x, it's not easy for us to find an inverse that would take things back. So to do this, I'm going to have to introduce a brand new function called a logarithm or a logarithmic function. And before I can get to those, I need to get you used to the notation of a logarithm. So we will pick up here next time. We'll talk more about this notation. We'll do some problems. And eventually we'll understand that the inverse of an exponential function is this logarithmic function. All right. And then we'll graph them and solve equations. All right. That's all I've got today. Anybody have any questions or issues or comments or anything? Okay, you all have a good day.
Alrighty, thank you, sir.
Okay. If anyone needs me, I'll be in my office hours at 11.